Next, let us try one more. The next one will be easy, but then, so I'm going to show a new theorem called pigeonhole principle. So this theorem has a name called pigeonhole principle. So what does it say? So it says that if k plus 1 or more objects are placed into k boxes, then at least some box, so at least one of the box will have contain 2 or more objects. So it's like, suppose that I have 6 balls, and then I want to put them all into 4 of the boxes. Then no matter how we put the balls, then some box will contain 2 or more balls. Is that okay? Okay? Straightforward, right? So, but then you may try to say that, okay, let's say we prove it in this way. So we have 6 balls. So on average, it is like 1.5 balls. Or you may say, in the worst case, each box has 1 ball, but then you have 6 balls. So in the worst case, so after you do the averaging, then one box must have 2 or more balls. Okay. Well, this proof has a correct flavor. So this is the idea how we are going to prove this. But some of the arguments is not correct. So we mentioned in the worst case. So why is it the worst case? Why is the average a worst case? So there can be many cases, right? So if all the boxes are distinct, so there can be what? There can be 4 to the power 6 cases. You put the first ball into one of these 4 boxes, and so on and so forth, right? So you need to show all the 4 to the power 6 cases to what? In each of these 4 to the power 6 cases, we still be able to find one box with 2 or more balls. So this should be the case where we are trying to prove in the direct way. Okay? So the proof that I just told you is not what? It's not precise. It is because we mentioned in the worst case. And why is it the worst case? Maybe the really worst case is that we put 6 balls in the first box. Then the first box is so crowded that it has 6 balls, right? Right? So in the worst case thing that we just mentioned is not making sense. Okay, although from your heart you know that this could somehow be the worst case. Okay. So to prove this, it turns out that it is also very easy. So the proof is by contradiction again. So we assume, to the contrary, that the theorem is wrong. The theorem is false. So what is meant by the theorem is false? So let's take a look. So what does the theorem says? K plus 1 objects or more put into the K boxes. So let's say this is the setting that we are considering. So if it is false, then that means what? Then that means that even though we have K plus 1 or more objects and exactly K boxes, we do not find this to occur. Okay? So at least one box contains 2 or more objects is not occurring. So what does that mean? You don't see any box with 2 or more balls. So what does that mean? So that is, so let me write down with k plus 1 or more objects and k boxes. We have, so we can have this not occurring. At least one box contains 2 or more objects does not occur. So that we can have all the boxes contain 0 or 1 object. Is that okay? At least one with 2 more. The opposite of them, of this one, is that each of the box has 0 or 1 object. Is that okay? If you are okay with this, could you please raise your hand? Okay, good. And then what do we get? So if this is the case, then what? Then this will, so 0 to 1 object. So how many objects do we have? Let's count it this way. We have k box. Each box has 0 or 1 object. So the number of objects from this case, the number of objects from this case that we know must be less than or equal to k. Does that make sense? Because we have k boxes, each box has 0 or 1 object. So the total number of objects from this statement must be less than or equal to k. Is that okay? And now we get a contradiction. So the contradiction comes from, we are saying that the total number of objects is less than or equal to k. But then at the beginning we have what? We are saying that we have k plus 1 or more objects. These two things are contradicting. We have less than or equal to k objects, and we have more than k objects. So we have 2 statements. One is the opposite of the other. They are derived under the same conclusion. They are derived under the same assumption here. So what does that mean? So it means that this assumption at the beginning has to be wrong. So the contrary assumption is wrong. So the opposite of this one will be correct. That means the theorem is going to be correct. Is that okay? Okay. So this is called the pigeonhole principle. And there is a generalized version of the pigeonhole principle. Let me also write it down. So this is a very simple thing, right? A simple theorem. But then it can have a lot of difficult theorem as a consequence of this pigeonhole principle. So we will take a look. Okay, so the general version. Okay. So this is the generalized version. So the generalized version, pigeonhole principle. So what is it? So again, we have objects and boxes. So if n, or so we write, rather than k plus 1, we write as n, or more objects are placed into k boxes, then at least one box. So let me ask you to try to get a magic number here. Contains Okay, let me leave a blank here, or more objects. So what should we fill in here? So let's say, not k plus 1, let's say 10, okay. So if I have 10 balls, 3 boxes, then what can we conclude? So 10 balls, 3 boxes, then we can conclude what? A certain box has 4, right? Looks like, using our worst case idea, right? 3, 3, then you still have a 4, right? Right? But how about 9? So if I have 9 balls, 3 boxes, then it could be 3. We cannot do more because it could be 3, 3, 3. How about 17 boxes? 17 balls and then 4 boxes. So what would that be? 5. Okay. How about 17 balls, 6 boxes? 3. Okay, so 17 and 6 you get 3. 17 and 4 you get 5, right? So what is the relationship? Yes, the relationship, you try to divide n by k, right? And whatever you get, so you try to divide n by k, and whatever you get, if it is an integer, then it will be just n over k. But if it is not an integer, you round it up to the larger integer. So we call this a ceiling function. Okay, so this is the ceiling function. Ceiling function brings a non-integer to the smallest integer greater than it. Okay, so the ceiling of 3 is equal to 3. The ceiling of 3.1 is equal to 4. So we can also define it for negative number. The ceiling for minus 2.1, it is equal to minus 2. Minus 2. Okay. Okay. Is that okay? So if it is integer, then it is integer. Otherwise, you move it up. So this is called the ceiling function. So the opposite. So we will have this one, 3.1. You get it, 3, sorry. So this will be 3. So you go down. And then minus 2.1, you go down. This is called the, so this is going to be minus 3. Is that okay? So this is called the floor. So the floor, the ceiling. Okay, you go up or you go down. Okay, so n over k. And then this is what we are trying to show. Okay, how do we show? The same method. But we still want to make some preliminary claims about this ceiling function. Okay, so n over k. This one must be less than n over k plus 1. Does that make sense? Yeah, because it is the ceiling function, right? But then on the other hand, it is greater than or equal to n over k. Okay? Okay, so this makes sense, right? Okay, now, so let's do the proof. So the proof here, by contradiction. So assume wrong. Assume to the contrary that the theorem is wrong. So we have m. So what do we have? So we can have n or more objects k boxes, and each box contains what? Contains less than or equal to this one objects. Is that okay? Does that make sense? Okay. So if each box contains less than or equal to this one, then this thing, we can also replace it by less than n over k. Does that make sense? If you take a look, n over k ceiling is less than n over k plus 1. So n over k ceiling minus 1 will be less than n over k. Is that okay? Right? So I minus 1 here. I take out this 1. So n over k ceiling minus 1 will be strictly less than n over k. Is that okay? Okay? Good. We put this back here. If this is correct, then you put this back here, it is also correct. So we, instead of saying that each box contains less than or equal to n over k ceiling minus 1 object, we can replace our argument to a weaker argument. We will say each box contains strictly less than n over k objects. Is that okay? 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 It's like I'm making a weaker argument. So let's say if I'm saying, oh, I don't have $100. I can also make a weaker claim. I don't have $1 million. Yeah, it is also correct, right? If I don't have $100, then I don't have $1 million. Although I don't have $100 is a stricter argument. It's a more tighter argument than the other one, but it's still okay. So because I know that this value is strictly less than n over k, so I'm replacing this, and the whole thing still is correct. Okay, so I'm going to replace it. Replace it. So I'm going to replace it by strictly less than n over k objects. Is that okay? And now we get the same contradiction. Because there are k boxes, each box contains strictly less than n over k objects, so we will have strictly less than n objects in total. Okay? But at the beginning, we are saying we have n or more. So n or more contradicts with strictly less than n. So this is the contradiction. So in the end, we find that k times n over k is equal to n, right? But we are having strictly less than n objects. So we get a contradiction. Okay? Okay, that's it. So why do we call it a generalized pigeonhole principle? Because if we know this, then we know that. We just put what? We just put n as k plus 1. So we put this one as k plus 1. Okay? So k plus 1 divided by k, if you take the ceiling, then this will be equal to 2. Okay, this is exactly the pigeonhole principle that we know. Okay, good. So we are going to look at a few examples next time. So we don't have time. But then let us take a look of this example that is not in the lecture notes. Let's see if you know how to solve it. Okay, so suppose that there is a tourist that goes to a place, that goes to a country and visit different places. So goes to a country. Okay, let's say these are islands. So you can take boat between different islands. So maybe there's a boat from here to here, and here comes. Okay, let's say boats are meant to be one way. Okay, so let's say if you can get a boat from here to here, you don't get a boat back. Let's say. Okay, and then so this tourist is going. So we don't know. This is the first time that he visits the country. He visits the country, and then somehow what? Somehow he knows that. He knows what? He knows that. So although he doesn't know this country, he knows very well that this country contains only 13 islands. Okay. So each day, let's say day 1 he arrives at a certain island, and so there may be boats to different places, but some of them you don't have boats. Maybe something like this. Maybe you have a boat here, you have a boat here, and so on and so forth. Then what he knows is that after 14 days, not 13, 14 days, then he will either discover that there is a certain loop in this country, or he will not be able to continue his journey. Does that make sense? Let me see. Yeah, war. Why? What is the reason? So some island you may not have any exit. So this is the end. So you don't. Either there is a loop that you can go from one island to island and another island and comes back, or after 14 days, then he will discover that he cannot move. Okay. Or no, before this 14 days. Maybe he's that unlucky, he's here, and then he gets stuck in the first day. Okay, by pigeonhole principle. So what does that mean? So by pigeonhole principle, so either he gets stuck, right? Either he gets stuck, or he does not get stuck for all the 14 days. So for all the 14 days, there are just 13 islands. So what does that mean? He must be visiting at least one island more than one time. Okay. If he can visit a certain island more than one time, then that means what? That means that there has to be a loop. You go from this island for the first time, and for some other day, you come back. So that means that there has to be a loop. Is that okay? So either he gets stuck, he cannot go anywhere, or there is a loop. Okay. Okay, this simple idea, this is a very simple idea, right? But this has some application in the theory of computation. So if we have a chance, then I will introduce to you some of the things there, okay, and then talk about. So so I will talk about more if we have a chance to talk about theory of computation here, okay. So let's end the class early for today, and then next week we will have a lot of examples of pigeonhole principle. Okay, that's it.